So let's instead look at a linear algebra approach to these basically stress transformations. So again, more circle, very useful, but I think we have a better approach. So we can actually transform our stress state. So one key thing here, this is not for 3D stress state transformations. We'll get to that in a little bit and discuss some methodologies to utilize that or to do that. But first, we can define our transformation matrix T. So this is our transformation matrix T. C is equal to cosine of theta. Again, rotation, again, only for plane stress states. S sine theta. And we can transform to a new stress state from an old stress state via this relationship, this T, this linear algebra approach. So you can see this kind of visually and similarly here. Again, whenever you're doing linear algebra, your dimensions have to match. So this is a column that's basically 3 rows, 1 column. This is a 3 by, basically 3 columns, 3 rows. And then if you dot that, it will produce basically a 1 by 3 again. So my new stress state is indicated here. This is my old stress state. And we can kind of go back and forth and actually use this to solve the problem. So how can this be useful for one? Let's say I want to answer my question of what's the rotation, right? How can I get to my principal stress state? Well, I'm going to pull up my handy dandy Mathematica. I'm going to quit the kernel because there could be some similar variables. So I know, for example, I can look this up here. I'm defining everything. This is my stress state, and then I'm going to put it in my notation of basically this 3 by 1 matrix. So how can I figure out where my principal stress state lies? Well, I can all I have to do, we could do this right here. Yeah, we could do this together. So if I'm in my principal stress state, that means my new stress state doesn't have any basically shear stresses. So that means if I do T dot stress 1, 2, or stress 1, 1, 2, you'll see that I have 3 equations here. So I could pull out basically equations 1, 1, 2, 3. This is the equation that gives me this sigma prime 1, 2. So if I'm in my principal stress state, I know that this value should be equal to 0. So give me the theta that achieves this goal. Let me zoom out a little bit. So I get a lot of nasty things, so I just want to look at it. Give me the numeric solution. And you see I have quite a few different values. Why do I have 4 values? Well, it's circular symmetry, so you can see on more circle, you could have 4 different rotations that lead you to the same answer. But what do you know? What's the angle to get to my principal stress state? 19.3299? That's exactly what we just solved for previously. What are my principal stress values? Well, let's see what happens when we plug in that angle. So let's put this in right here. And you see 16.4 again, 3.6 again, and then you see this is super, super, super small. It's basically 0. It's just Mathematica is having a hard time on getting that value right. But we found our principal stresses, and we found our principal stress state, the rotation, just like we did previously. But look at how we did this. 1 line of code, right? And you could modify this and change this for different stress states. And then you could just plug in right here. You still keep the intuition, but we're just solving it like a math equation, which is what we as engineers always want to do. So let's take the same approach and go a step further, right? So this is my equation. So if I want to maximize my shear stress, to find my location of maximum shear, I need to take the derivative of this. I need to find maximum of a function, right? So take the derivative. I'm going to solve. When does this equal 0? Solve it for theta. And do it numerically. Always forget. Not little n, capital N. And then I could find that rotation. And you can see this is my, again, negative values of clockwise rotations. Remember what we said previously? We said in the last video that to find that rotation, it was going to be 90 minus 2 times our 19.392. So this is our rotation in 2 theta space. We have to divide this by 2 to find the real space, and we'll see that it matches. So that's the rotation angle that's required to find our principal, or actually our maximum shear stress state. Let's look at the values. Remember, it was like 6.4 something. So now if I go to this angle, I can find, again, look at, our stress state is centered at our center, and we find that 6.4 values again. Now here's the rub. Here's the real beauty though. Now what I can do, I can answer that previous question quite easily, right? What is the stress state at a clockwise rotation, minus 15 degrees clockwise? What's the new stress state? Let's look at this numerically. There it is. That's it. We've got it. We have those values. And you see here, and we'll kind of grab it, those match exactly what we saw previously. 12.33, 7.66, 5.96. Look at the lines of code that were required to solve this. All those questions. 1, 2, 3, 4, 5. That's it. So efficient, not only reproducible, but you can do this quickly, and it allows you to still maintain your intuition of the problem. That is amazing. That is fantastic. So next time we'll go through the same kind of approach for strain, and it's going to be the exact same thing, same math. It's just you'll have to think about strain space and then normal strain and then engineering shear strain. So thanks. I'll see you next video. Bye.